So this chapter we shall be talking about chemical reactions. Which chemical reactions? Combustion, right? Not every chemical reaction. The chemical reactions which relates to combustion. Because in the previous chapter we have studied so many different cycles: auto, diesel, gas turbine, jet engine, or we shall study steam power cycle. So in all those cycles, there was one process in which fuel is burnt and heat is produced, either in gas turbine or in auto diesel cycles. With the help of that spark, fuel is burnt, energy is released. So now we shall discuss this particular process in some detail in this chapter, because the burning of that fuel is actually a chemical reaction. So we'll study how this chemical reaction takes place and how to calculate the energy which is produced by burning a fuel, what is the maximum temperature which can be obtained by burning a particular fuel. Okay, I'll be a bit quick because we have very less time to cover the course. So this basic theory, I will not go into much detail. You can also read it by yourself. So let's quickly go through these simple definitions. What is a fuel? Any material which can be burnt and to get heat energy out of it, then it is called fuel. Okay. So the most commonly used fuels which we are using in various applications, all of them are actually different composition, different combination of hydrogen and carbon. So in general, we call them hydrocarbon fuels, and this is the general formula for them. Okay, like CH4, C2H4, C3H8, and so on. So these fuels which are available, those could be in different phases. For example, those could be solid fuels like coal, those could be liquid fuels like gasoline, diesel, etc., and those could be gaseous fuels. So those fuels are available in different phases naturally. In normal ambient conditions, those could be solid, liquid, or gas. For example, the coal, the major element, the major part of that coal is consisting of carbon. But there are also other components, the other elements like oxygen, hydrogen, nitrogen, sulfur is also there, moisture is also there, and ash which does not burn or which does not react. Composition of coal that may vary from location to location from where we are extracting coal. Next, liquid hydrocarbons. Most of those liquid hydrocarbons, those are obtained from crude oil. So what is crude oil? The oil which we get from the earth in raw form. So in this crude oil, from this crude oil, we extract different fuels by burning it. By burning it, so the most volatile, whose evaporation temperature is least, will evaporate first, and that is actually gasoline or petrol. The next is kerosene. This is a fuel which is normally used in jet engines. This we know, cars and automobiles, right? Diesel fuel, the next one which will be obtained is normally diesel. Its applications are huge, not only in automobiles but also in power plants, right? And all the heavy machinery. Electric generators, those are also made up of diesel fuel. Fuel oil, another one, the most dense or the most heavy one amongst all, is this fuel oil that is also used in marine applications, ships, boats, etc. But that creates more pollutants than the others, so that's why its use is becoming less and less. But still, that is also type of fuel which is used not only in marine applications but also in power plants or to produce heat for space heating during winter, etc. So these are the liquid fuels which we obtain through a process which is called distillation, right? That's a complete separate topic which normally chemical engineers they study in more detail. this distillation process. So these are the commonly used liquid fuels. There are other liquid fuels we will see in the next slide. The most volatile, means which is easily evaporated, is the gasoline, right? And next, the less volatile are kerosene, which is normally used in jet engines, diesel, and fuel oil. Okay. So the composition of this, out of this crude oil, again depends upon the location from where we extract that crude oil. In some cases, with crude oil, you will also have gas, natural gas, CH4. So gasoline or petrol, its chemical composition is C8H18. For diesel, it is more heavy or more dense. So it's C12H26, right? Another liquid fuel which is used, not very commonly, but still it is also potential to be used as a combustion fuel, which is methyl alcohol. It produces less pollutants compared to diesel and petrol, or else also called methanol. Then for gaseous hydrocarbons, the most common one is CH4 or methane, which is also produced from those gas wells or oil wells, right? The composition of natural gas is mainly methane. 80 or 90% is methane. The rest could be small amount of ethane, propane, hydrogen, so many other small constituents are also there. If you want to use it in vehicles or you want to transport it from one location to another location, so we have to convert it in liquid. So if you want to convert this natural gas into liquid, so its temperature must be dropped to up to minus 162 degrees Celsius, so that it can be converted into liquid form, and then you can transport it from one location to another. But then it is called LNG or liquefied natural gas. There is another type of gaseous fuel which is called LPG or liquefied petroleum gas. It's not CH4, it's propane, C3H8. Its chemical composition is C3H8, propane, mainly propane, but there is small amount of butane or something else, but 90% is propane. This gas is much dense than natural gas, and also if you compress this gas, it converts into liquid. Okay, so those LPG cylinders, those have actually that LPG gas in liquid form because that is under pressure. So as the pressure is released, when you open the valve, the liquid immediately converts into gas. That's why it is called liquefied petroleum gas, because under compression it is in liquid form. It is more dense than natural gas. It is also denser. Its density is more than normal air. So if there is a leakage of LPG, it will be stays down. But if there is a leakage of natural gas, it will diffuse quickly into the air. So that's why the leakage of LPG is more drastic or dangerous than this one, natural gas. Yeah.
Does natural gas and LPG have smell?
No, natural gas, I'm sure it is there. There is no smell. We artificially add that smell so that we know that there is a leakage. LPG, I'm not sure it has a smell or not. Okay. So these are different types of naturally available or most commonly used fuels. Okay. What is the problem with these fuels? When you burn them, they produce gases. Some of those gases are not good for our environment. They are a source of greenhouse. They are a source of course, some of those gases are poison for us. So that is the major issue with these hydrocarbons, because they may produce nitric oxides, which is a poisonous gas, carbon monoxide, another poisonous gas, and some other hydrocarbons. And the major part of any of these fuels, whenever this hydrocarbon will burn with oxygen, one of the component will be CO2, and that is greenhouse gas. Okay. That's why there is always people are looking for alternative fuels which will give you less pollutants. For example, in this table you can see this ethanol, methanol, CNG, LNG, they produce less pollutants compared to petrol and diesel. But the issue is here, the energy which is produced by burning these fuels by 1 liter, by 1 liter consumption, they will produce less energy compared to these one. That is one issue. And here it is written in terms of ratio, in terms of gasoline equivalence. So for gasoline, if this ratio is 1, you need 0.96 of diesel, light diesel, to get the same amount of energy as produced by gasoline. But here you can see, for example, this one, methane, you need to have 4 times more methane to get the same amount of heat as of gasoline. So here it is in terms of gasoline equivalence, the comparison is given. So although those fuels are less pollutant, but they also has less energy per liter. Yeah. Greenhouse means what? Okay, here is, quickly, I cannot waste time on this thing. Earth, atmosphere, sun, here is the sun radiations entering, this is En, the same thing in the En. Now Earth starts to emit radiation, because when every body whose temperature is above 0 Kelvin is emitting radiation. So by absorbing this energy from the sun, the earth temperature starts to rise, so it starts to emit radiation back, right? So E in should be equal to E out. This is E out. Then the temperature of the earth will be constant. Now the issue is that E in is not equal to E out, because in this atmosphere we have CO2. What the CO2 does, it absorbs this radiation emitted back. We'll discuss this radiation in more detail in heat transfer. Okay, what is this? This is short wave radiation, this is long wave radiation. Those are different nature radiation. So CO2 does not absorb this radiation, which is short wave, but they absorb this radiation, long wave radiation, if there is too much CO2 present in the atmosphere. So it means this energy which is emitted by the sun, it's not going into the space. It is trapped here in this atmosphere. That results in the rise in temperature of this earth. So this rise is not so huge, it's only 1 to 2 Kelvin in last few centuries, and that 1 to 2 Kelvin average temperature rise is responsible for all those weather changes, etc. So that is called greenhouse effect. The energy which is trapped in this atmosphere, which cannot go into the space, that trapped energy will rise the temperature of earth, because E in is not equal to E out. There is E in minus E out is equal to energy which is getting stored here, right? That is the responsible for the increase in temperature of earth. Yes, radiation absorbed by these gases, greenhouse gases. One of the major greenhouse gas is carbon dioxide, which is produced, not only carbon dioxide, there are other refrigerants which we use in these air conditioners.
And they're not changing refrigerants.
Yes, now they are changing, but the damage has been done already. And still, there are many countries who are using those old refrigerants. Okay, let's quickly. So we discussed this thing. Now let's quickly go to the next one. Now, what is combustion? Combustion is any chemical reaction in which some any fuel, for example, this fuel, methane, will react with oxygen and will get heat here, and C will react with oxygen to make CO2, and H will react with oxygen to make H2O. Okay.
Ignition stuff
Ignition, that is also when that ignition temperature is there, only then this reaction will take place. So combustion is any reaction between a fuel and oxygen. So oxygen is required to burn any fuel. That chemical reaction, that particular type of chemical reaction is called combustion. And heat is produced, heat is released from this fuel. And this oxygen is called oxidizer. This, what is the source of oxygen? Air. So it means if we are taking oxygen from the air, so it will not be pure O2, there will be N2 and other gases. So it will be air. So in that air, oxygen will react with this fuel. Okay. So for example, if 1 mole of air, a certain amount of air I have, in that air there will be 20.9% oxygen, 78% nitrogen and other amounts, argon and some other gases. For combustion analysis, we will assume that it is only 20%, it's just consists of two parts, 20% oxygen and 79% nitrogen. What this mean? 0.79 divided by 0.21 is 3.76 moles of nitrogen. What this mean? If there is 1 mole of O2 in air, it will have 3.76 moles of nitrogen in it. This means this is 4.76 kilomole of air. If you want to have 1 kilomole of oxygen, it means you should have 4.76 kilomoles of air. That will ensure that you will have 1 kilomole of oxygen along with 3.76 kilomoles of nitrogen from here, from this ratio. Okay. So always 1 kilomole of oxygen will be accompanied by 3.76 kilomoles of nitrogen, which means you will have 4.76 kilomoles of air, which will give you 1 kilomole of oxygen. If you need 20 kilomoles of oxygen, means 20 kilomoles of oxygen if it is required for any chemical reaction, it means there will be 20 into 3.76 kilomoles of nitrogen, because you are taking this oxygen from air. So it means you need to have 20 into 4.76 kilomoles of air to have 20 kilomoles of oxygen, right? So it is mentioned here. Where we have pure oxygen. In normal air, we are using this air, and by next we will solve chemical reactions. To burn this much amount of fuel, I need this much oxygen, but this oxygen alone is not present. This oxygen is always present with this much nitrogen. Yes, there they produce oxygen, they extract oxygen, they store them in a cylinder in liquid form, and then they take it. But for normal combustion at ground level, yeah, we are neglecting. They are in 1%. They are 1%, so we are neglecting them for our calculation of this combustion. Okay. So during combustion, nitrogen will not react. During normal combustion reactions, nitrogen does not react. It's only oxygen which reacts. Okay. So the nitrogen, when it doesn't react, it is called inert gas. Inert means it does not react. Okay. During a chemical reaction. And this air, we do not have dry air all the time. What else we have in it? O2, nitrogen. The remaining we are neglecting, but there is H2O in vaporized form. Okay. Moisture. Okay. So during chemical reaction, only oxygen will react. These two normally do not react, but they will appear here. So this H2O, which was present in air, that will be here, plus H2O which is produced during this chemical reaction. This hydrogen will react with oxygen, you will have H2O, and this H2O as it is. So you will have more H2O in the combustion products. Okay. Next, moisture in this H2O will be considered as inert. It also does not react like nitrogen.
Well, we consider the 21% of oxygen and 79% the moisture is not added.
No, we'll do some problems, then we'll add moisture in it. Yeah, the amount of moisture in terms of kilomoles or in terms of kilogram is very small. But if it is very humid air, then we cannot neglect that. So we'll be solving problems. Yeah, then we'll add that part. How? We'll see. Okay. During chemical reaction, of course, temperature increases to a very large value. If the temperature reaches a very high value, then there is a possibility that this H2O will dissociate into H and O or OH ions, or nitrogen may react with oxygen to produce nitric oxide, which are poisonous gases. We want to avoid those, but that is also in actual combustion, there are so many things happening. So here we'll see what is ideal combustion, which we want to achieve, and what is actual one. So in actual combustion, you will have CO here, unburnt carbon, only C if this chemical reaction was not proper. The proper amount of air was not supplied to burn this. Too much air is supplied or too less air is supplied, then you will have so many other constituents. So actual combustion can have many other constituents in the product gases. Okay. So for example, here you have a steady flow chemical reaction. So here, for example, in this case, this is CH4 and oxygen, but here he is taking the example of carbon and O2. It is reacting to give you CO2. During reaction, some heat is produced. So this part is called reactants. On this side, we call it products. Okay. During any chemical reaction. And when this combustion will occur, if the temperature here, starting temperature is ignition temperature of that fuel, and every fuel has its different ignition temperature. For example, for petrol 260, for carbon, pure carbon temperature, initial ignition temperature, and for other gases it's given as an example. So ignition temperature is important, then proportion of air and fuel. How much air must be there to burn a certain amount of fuel? So this proportion should be proper to make that combustion occur. If this proportion is not important, combustion will not occur. For example, if you want to burn natural gas, CH4, it will not burn if its concentration is less than 5% in air or greater than 15% in that available air. If the proportion of this nitrogen is between these two ranges, only then it will combust properly. Look, for example, there is this much 1 kilogram of air. So there must be 5% of this air as CH4. 5 or 15, between 5 and 15. So proper proportion should be there for this, for its combustion. If too much air or too less air, then combustion will not take place. For example, how you combust natural gas at home. Okay, but if you want to, if you have too much air, it will go off. Why? Because there is too much air. It is combusting with air, but a proper amount of air, normal air. If you have a fan there, then it will not be a proper combustion because there is too much air compared to the fuel.
So
okay.
If I do the fuel and the natural gas go to be less than 0.5.
Yes, you are increasing the amount of fuel, and amount of air is not restricted, that is present, right? The amount of air So more air will start to flow
If I have
towards it.
small fuel leakage, it will not burn.
No, it will not burn. Yeah. First of all, you need ignition. Without ignition, it will not burn. Okay. So for ignition, you need to have. Thanks God, it doesn't burn without ignition. Otherwise, whenever there is a leakage, there will be blast. So you need some ignition. Okay, so let's move on because these are just the basic theory. Based on this, we will be solving problems. Okay, so whenever we have this chemical reaction, we need to balance this. So if we know how much reactants are there, then I should be able to calculate how much will be the products there. Okay. So the total amount, so what is the principle here? That the total amount of mass on reactant side will be equal to the amount of mass on the product side. So the mass will remain conserved during this process. Okay. And also in other words, the number of atoms on this side of carbon will be equal to the total number of atoms of carbon on this side. Although here carbon was CH4, here carbon becomes CO2. But the number of atoms of C here and here will remain same. So the number of atoms on both sides of the equations will remain same. The total number of mass of every element on both sides or the total mass will remain same. But what will change? Moles. Moles will not be same on both sides. The total number of moles here may not be equal to the total number of moles here. Now let's try to understand with the help of this example. Hydrogen is reacting with oxygen. So how much hydrogen, 2 kilogram of hydrogen is reacting with 32 divided by 2, 16 kilograms of oxygen. So you will get 18 kilograms of H2O. So 2 plus 16 must be equal to 18. Okay, so the total mass is same. But what about the, okay, atoms here? 2 molecules, 2, 1. Moles. So where is mole? 1 mole of hydrogen is reacting with half mole of O2 or 1 mole of O. Half mole of O2 or 1 mole of O. And what we are getting, so here we have 1 mole of O, 1 mole of hydrogen, and here we are getting 1 mole, not 2 moles of H2O. Here we are getting, so here number of moles are more, here number of moles are less of H2O, not H2 and O, because those are combined. So the number of moles have changed.
Why don't we say that 2 moles of hydrogen yields 2 moles of hydrogen? 1 mole of oxygen yields 1 mole of oxygen, so it's conserved.
Yes, individually is conserved, but I am saying total. 1 of this plus 1 of this is not giving me 2 of H2O. It's 1 of H2O.
So when they say total,
total is not conserved, total mass. Yes. So mass will remain conserved, but total number of moles is not conserved during a chemical reaction. Okay. So yes, you're right, total number of moles. So example is here, this is clear, this is atomic number, this is important for us. What is this number? Atomic mass, in other words, that represents kilograms per kilomole. That is the molar mass of that element. Or it can also be written as grams per mole. It's the same thing, kilograms per kilomole or grams per mole. Okay, let's move on. Some terms which are important in combustion study. Air fuel ratio, we have talked about a bit in previous chapters. So for example, to burn 1 kilogram of a fuel, we need 17 kilograms of air. Why? We will see later on. We will calculate to get 18 kilograms of product. So here the air fuel ratio is 17 divided by 1. That is called air fuel ratio for a complete combustion. Air fuel ratio, and it is represented in terms of mass ratio, not in terms of moles ratio. Always in mass we represent this air fuel ratio. In some cases they also use fuel to air ratio, so the reverse of this. The reciprocal of this is fuel to air ratio, right? And the relation between mass and number of moles. This will be used quite extensively in this chapter, so this should be clear. I hope this is clear. Number of moles multiplied by molar mass will give you the mass. Let's solve one question. Now here we have 1 kilomole of octane, that is petrol, gasoline. So 1 kilomole of C8H18 is burnt with air that contains 20 kilomoles of O2. So it reacts with air, means in which we need 20 kilomoles of O2, means there will be, with 1 kilomole of O2 there will be 3.76 kilomoles of nitrogen. So it means 20 kilomoles of O2 will have 20 into 3.76 kilomoles of nitrogen. And this is what, 4.76 kilomoles of air. So yeah, I already explained it to you. So 20 kilomoles of oxygen means 20 into 4.76 kilomoles of air is required. Okay. It reacts as shown in the figure, and what we get as a product, CO2 H2O plus O2 plus N2. How many number of moles we want to find out? Here the number of moles on the reactant side is given. Here it is not given, so that is represented as X, Y, Z, and that for nitrogen he is using W. Okay. Is it a complete combustion?
No.
Why? Yes. Complete combustion means all the carbon will convert to CO2, all the hydrogen will convert to H2O, and nitrogen will be as it is. But here you see extra oxygen, so this is not an example of a complete combustion, right? So they found out from these exhaust gases there is also pure oxygen. Now we can find out the number of moles of each of these. So make, yeah, nitrogen will be same. So we need to find out these X, Y, Z, and W, moles of these exhaust gases. So it is by mass balance. So let's start with carbon. 8 here is equal to X. Only there we have carbon in CO2. Next, hydrogen balance. So you will write H balance, so 18 must be equal to 2Y because it's hydrogen. Okay. So from here Y is 9. Next, oxygen. O balance or O2 balance, it's up to you. So you can write it as O, O2. Okay, O2 is how many O2s are here? 20 kilomoles must be equal to X. Now you said O2 balance, so only X plus half Y plus Z. Or if you write O balance, 40 is equal to 2x y z, oh yes, 2z. So we'll get the same answer. So it's up to you how you balance. O, next N2. Let's use N2, not N. Yeah, 3.76 into 20 equals to W. So from here you can find out X, Y, Z. So that will be the number of moles of exhaust gases. Okay. Next, we need to find out air to fuel ratio for this combustion. Means M of air. So air to fuel ratio, M of air divided by M of fuel.
molar mass times the number of moles times
So molar mass of air multiplied by number of moles of air.
molar mass.
So C8H18 means 8 kilomoles of carbon multiplied by 12 kilograms per kilomole of
Plus 18 times 1.
yes plus 18 times 1 for hydrogen. This is carbon. What is molar mass of air? Remember?
Molar mass 4.4.
29 kilograms per kilomole for molar mass of air multiplied by
4.76 times 1.
yes 4.76 multiplied by 20 kilo mole. Now kilomole, now you have kilograms, and here it must be kilograms. Kilograms, this is kilomole, so mole will cancel with mole. It's kilogram over kilogram. 29 mass, the molar mass of air. Memorize it for air.
Given.
Should be.
Molar mass of air 29. For nitrogen it's 28, I think.
Okay.
Yes, 14, but N2 28, so it's near to nitrogen. So that's how you can remember. So here is the air fuel ratio for this question, and here air was a bit higher. That's why you had unburnt O2. Okay, so this question was just to find out the how to find out the unknown moles of product gases when for the reactants it's given. Okay, so we'll have some more complicated problems later on. So it's just the start. So now let's.
You said that complete combustion is that the carbon and the fuel reacts completely to CO2.
Yeah. Yes. What that statement means? Complete combustion.
Explain more.
Okay. So any substance, that is the definition. If the carbon in the fuel burns to CO2, all the hydrogen in the fuel burns to H2O, and if there is sulfur present, it must burn to SO2. For example, CH4 plus O2. So C must react with CO2 and H must react with to form H2O to get maximum heat. If does not react completely, then you will have CO or O. Reaction was not complete, so that's why some of the carbon does not react fully to give you maximum heat out. That converts to CO. Or some of the oxygen, you supplied too much oxygen here, so that's why some of the oxygen is appearing here as unburned. Or some of the hydrogen does not react fully with oxygen and we get HO or H. These are incomplete combustion. So incomplete combustion will have these things. Complete combustion means all of the carbon converts to CO2, all of the hydrogen converts to H2, and we get maximum heat out of it, and there will be no unburnt or such half-burnt things in it. That's what it means. And in coal you also have as sulfur in coal. So you must have sulfur in the form of sulfur dioxide. If you have sulfur as it is, it means sulfur did not react. You didn't get the heat out by the reaction of this. Okay. So that's what we call as complete combustion. So So everything in this fuel, every element reacts with oxygen to give you something. Nitrogen will not react, that will appear as it is for a good complete combustion. Okay. Incomplete combustion will have all these possibilities. You may have carbon, some carbon as it is, soot, carbon, solid particle. Okay, that is called incomplete. The reasons of incomplete combustion are so many. Insufficient oxygen, insufficient mixing in the combustion chamber, mixing of fuel and air, the ignition temperature was not achieved properly, and if during combustion temperature becomes so high that it will make this H2O to break into H into O and so on.
It will absorb the heat.
Yes, because some of those reactions are endothermic actually. So that's why there are many reasons of incomplete combustion. So whenever there is a chemical reaction between fuel and air, or in terms of fuel and oxygen has more tendency to react with hydrogen present in that fuel. So it will be ensured that hydrogen will definitely react with O2. Maybe some carbon does not react, or carbon will convert into CO, or as it is C. But one thing we can be sure that hydrogen will definitely react with with the oxygen, or all the hydrogen in that fuel will react with oxygen. If there is deficiency of oxygen, so carbon will not react fully, but hydrogen will definitely react with oxygen. Okay. So hydrogen in the fuel normally burns completely to form H2O, right? Some of the carbon may end up as CO or plain carbon. Okay. Then there are more terms. Now we know what is complete combustion, what is incomplete combustion. Now the minimum amount of air which is required to completely burn the fuel, that minimum amount of air is called stoichiometric or theoretical air. Stoichiometric or stoichiometric, I don't know, whatever this term. Okay, stoichiometric. Chemically, so it means 100% theoretical air. We can name this stoichiometric air as 100% theoretical air, which will make sure that all of the fuel is burnt. So that combustion will be known as stoichiometric or theoretical combustion. Okay, so the term stoichiometric is something. So for example, here methane reacts with air and to give you only CO2, H2O and N2. Look, you can find out this too if it is unknown, air theoretical, to give you only CO2, X, Y, Z. You can easily find out this X, Y, Z by assuming complete combustion. So after doing that mass balance, these are calculated, 2, X, Y, Z. So this is an example of a complete combustion. There is no unburned fuel, no free oxygen in the products. So it means here the stoichiometric amount of air is how much? 2 into 4.76 kilomoles. 4.76 kilomoles of air. That is air. 4.76 multiplied by 2. So that is the theoretical amount of air required to burn this fuel completely. Okay. In actual combustion, that is the minimum amount which we have calculated from this chemical balance. In reality, what you do, you supply a little larger than this. Okay, so that to ensure that the combustion will be complete, and of course there will be some unburnt air. unburned oxygen and nitrogen which will appear in the exhaust gases. You will always ensure a little higher, not less. Less means deficiency of air. Deficiency of air will result in CO, most probably. That is poisonous gas. So you always, to avoid this thing, you always send more air than stoichiometric or theoretical air.
When there is excess air, excess oxygen is required. It is called a combustion equation, not a stoichiometric equation. Or a stoichiometric equation is also a combustion equation.
Stoichiometric equation is a combustion equation, but if there is excess air, then still that is combustion, but that is not theoretical combustion or stoichiometric combustion.
So both the theoretical and the actual are called combustion.
Combustion, yes, because in both you are getting heat, but in one you are ensuring. But in reality, you will not be supplying exactly this amount of energy. In reality, there are so many other variables which you cannot predict. So to avoid these, you send more air than that. So excess air, for example, if you remember in the previous chapter in gas turbine cycle, we were discussing we send more air, that a part of it will burn, the remaining will, what will do? It will cool as a coolant. So what we are sending excess air. So this is called 100% theoretical air, but if I send 50% more in it, then I'll say 150% theoretical air. This is 100% theoretical air, which we calculated for this chemical reaction. And now I can add 50% more in it. So I will say 100 plus 50, 150% excess air, like here. 50% excess air also means 150% theoretical air. If you are sending 200% means 200% of this. 200% of this, for example, 2 3s are, it's almost 7. So multiplied by 200% plus 7. And the 7, I am adding 200% of this. In other words, this is 300% theoretical air. It means the same thing. So in the exam, if it is given as 150% theoretical air, it means 50% excess air. Excess of what? Excess of theoretical or stoichiometric. Deficiency, if there is 90% theoretical air, it means there is 10% deficiency. Out of that 100, 10 is less. 90% theoretical air means, yes, combustion will be there will be combustion, but there will be unburnt carbon or unburned hydrogen will appear here if it is incomplete combustion. So these are the concepts or definitions which should be clear when we'll be solving questions. In some questions, excess air will be given. In some questions, stoichiometric air. In some questions, you will see we'll add moisture here. This air has this much moisture in it. Okay. So we'll see in coming chapters.
There is 100% theoretical
Air, 100%. Okay. What is this? Okay. Before it's before after. Okay. What will be the composition of products for a complete combustion? We know there will be CO2, H2O, or N2. That's all. For incomplete combustion, it is very difficult to find out theoretically what will be the unburnt things there. So that's why with actual combustion, it is impossible to predict the composition of the products on the basis of mass balance alone. Then there are some experimental methods to find out the actual composition of product gases which we are getting. One of them is called Orsat gas analyzer. One of that experimental technique is called Orsat gas analyzer. What we do in that one, you can see videos on YouTube, Orsat gas analyzer. For example, from the combustion gases, here's some combustion chamber, air, fuel. Now these are the exhaust gases. Now you make these exhaust gases to flow in this Orsat gas analyzer. In this Orsted gas analyzer, if I remember correctly, there are such vessels, number of vessels with different chemicals in it. And here you have some water tank, something. So initially those are closed. So this gas will continue to flow here in this water column. It will be present here above the water, and here so once this gas is a sample is collected, now this is closed. All these are closed, and here we have different chemicals. Here what we do, if I remember, you increase the pressure of this water, it will make this this gas to flow in this column, and you will, for example, open this one, and here you have a chemical which can absorb CO2, only CO2. So this gas will flow here, it will stay here for a certain time. So here whatever CO2 is present will be absorbed by that fluid, and then you will close it. Then you will open this one so that the remaining whatever is there, H2O, will be absorbed here, and so on. So that's how you can, and here you will measure the weight before and after, to know before and after. Before and after, now CO2 is released, now the volume is dropped. So it means 0.1 liter was CO2 which was absorbed. So this is such experimental technique. Yeah.
Why we need to know the amount of
Just to, yes, if your engine is not giving the proper power, so it means combustion is not proper. One of the reasons is combustion. So when you analyze this exhaust gases, then you will know your fuel is properly burnt or not.
because you can just know the amount that you will need to provide, not need. The products, why are they important?
To know if your combustion is proper or not. Proper combustion means here you should have only CO2, H2O, and N2. If your combustion is not, you are seeing some smoke, colored smoke, it means some oil is burning, etc. Or too much air is, or deficiency of air is going. And how to know that? By analyzing the exhaust gases. By analyzing the exhaust gases, you will know, now I have CO2, but I also have certain amount of CO or certain amount of H present. That will tell us my combustion is not proper. And then I need to find out the reason why there is CO or H. Maybe air is in excess or air is deficient. So only by analyzing the combustion products, I can predict what is wrong here, what is happening here, what is wrong in this combustion chamber. So in actual combustion, how to do it, that is one technique, experimental technique. So I do not remember the complete detail, but that is available. Okay. So now we'll solve some problems which are important for exam. So these problems which we'll solve, one of them will come in the exam, in final exam. So whatever we have discussed so far, that knowledge will be used here to solve these problems. Okay.